So at the end of the last lecture, we were talking about thread pools, and I think we managed to get through sort of the general description of the interface that's provided by this thread pool class, and we just left off where we're about to talk about the application below that was using it, just a very simple application. So if we look at the application, this main function here, again, it's using the thread pool class from above. What we do to begin with, we're going to create a thread pool object, and again, the constructor specifies the number of threads that are created for the thread pool. So the thread pool basically creates all of the threads when the constructor is invoked, and then at the time that the object is destroyed, it will get rid of all the threads. So we're going to construct or create 8 threads in the thread pool. And then what we're going to do is we're going to loop 10,000 times, and we're going to invoke this scheduling function. Again, the schedule function, the schedule member function of the thread pool, all this does is we provide it with essentially a callable entity, in particular a callable entity that takes no arguments and returns void, or something that's compatible with this signature here. In this case, we're using a lambda expression to get such an object. Basically, it takes no arguments and returns void, and essentially what it does is it prints hello world. And we're going to schedule this task many, many times, basically 10,000 times. And this is going to get assigned to the various different threads in our thread pool. And then at the very end here, after we've done the loop, because it's quite possible that we could come out of this loop, but some of the threads are still running some of the tasks that we provided. So we want to make sure that they all have a chance to finish what they're doing. So we call this shutdown member function. And what this will do is it will block until all of the tasks that are currently running in the thread pool are done. So we can make sure in this way that we don't basically terminate the program by exiting from main until all of the threads are done doing whatever they're doing. Any questions?
But would it be fair to overload schedule with exactly the same as it is, except with null value reference? So we have 2 schedules, one with R value, one with null value, or do you generally just want?
Well, I mean, there's nothing really to prevent us from doing this. I suppose if you overloaded it with an L value reference, I think what we'd want to do is overload it to take a const L value reference, most likely. Because if we said just a regular, like an L value reference, but not L value reference to const, the reason that we wouldn't make it const is because the function's going to change it. And if the function's going to change it, then why not just use an R value reference instead? Because that's kind of making more clear that, hey, if you want to mangle the value of this thing, go ahead, make my day. Does that answer the question? Okay. Mm-hmm.
So you can actually just pass a regular function pointer into that and as a parameter, and it'll all work out.
Yeah, if you give it anything other than a std function, it's actually going to have to convert it to a std function, and then a std function, that temporary object would be what gets passed. It's not necessary to use a lambda expression here. We could, for example, create a functor class ourselves and overload the function call operator. But the important thing is it would have to be something that can be called such that it takes no arguments and returns void. As long as it has that call signature, we could create our own, without using a lambda expression, create our own functor class, or we could use a function pointer, like a pointer to a function that has, the type of the pointer type of the function it points to has the same signature as this. Basically, the function takes no arguments and returns void. So we have a number of different ways that we could use the schedule function here. In some cases, if the expression is an L value, you may have to do it like std move to cast it to an R value so that we can invoke this function because it's passing by R value reference. Any other questions about this example? Okay. So that kind of brings us to the end of the concurrency material for the course. So now we're jumping into another section of the lecture slides, talk a little bit more about resource management. And mainly the main resource that we're interested in this course is predominantly memory. That's sort of the most common resource. I guess to a lesser extent, things like mutexes and so on, these are resources. Anyway, maybe I'm getting a little bit ahead of myself. So a resource is basically something, you have like a limited number of them in the system. It's a limited thing. So you want to be careful that when you're done with these things that you release them and give them back to the system so other processes can use them, for example, other processes, other threads. So there's lots of things that might be considered resources, things like memory, files, devices, network connections. As far as what we're concerned with in the course, predominantly what we're dealing with is memory, kind of in general. That's the most commonly used resource. Also, we're doing stuff with threads and locks. These are other types of resources as well. Like when we're done with a lock, we want to make sure we release it. Like a mutex, we release it when we're done. Otherwise, we might cause a deadlock or some other sort of problem. So one of the common types of problems that you can have in code in general is a resource leak, which is the special case of is memory leak in the case that the resource we're talking about is memory. But more broadly, you can have any type of resource be leaked. For example, we could have a mutex, we acquire it, we never release it. Well, then this is going to cause problems because other threads, when they try to acquire that mutex, they're going to basically sit there forever because we're never releasing the mutex. So in general, any sort of resource leak can be problematic. It's just different types of resources will cause different types of problems when you leak them. And resource management is essentially a big issue because there's lots of bugs that can arise from not managing resources properly. And again, one of the main things we want to avoid are resource leaks. So some of what we're going to be talking about subsequently is dealing with the issue of resource management generally. So just to give an example of a resource leak where the particular resource involved is memory. We might have encountered this example earlier in the course, I'm not sure. But anyways, if we did, it was probably long ago and I can't remember, and I doubt that you would remember either. So let's treat this as if it was new. So what we have in this particular example is a function called useBuffer, and basically the intention here is the caller has to provide some buffer which is at least 1024 characters in size, and this function does something with that buffer. What it does doesn't matter, it's just represented by the ... here. An important thing to note though, this function useBuffer is not declared no except. There's no except in the declaration of this function, so this function is not promising that it won't throw exceptions. In other words, it may throw exceptions. And then what we're doing is we have this function called doWork, and what it's doing is it's creating a buffer because it wants to, whatever this useBuffer function does, it wants to use that functionality. And because the caller has to provide the buffer, it's allocating a buffer of size 1024 characters. Then it's passing a pointer to this buffer into useBuffer, and then after the function call returns, the code is being very diligent to make sure that it releases the resource that was allocated. In other words, it's freeing the memory. But of course, this code is badly broken because the useBuffer does not promise it won't throw exceptions. If it does throw an exception, what will happen is because there's no try block or anything, there's no attempt to catch the exception in this function doWork. What will happen is if useBuffer returns due to an exception being thrown, you'll just propagate out of the function doWork without ever hitting this line that deletes, that has a delete expression on it. In other words, you'll leak the memory. So this is a very kind of brittle way to write code. And essentially what we want to look at in a little bit more detail is ways to combat this sort of problem. So if we look at a more general sort of pattern, or I guess it calls it an anti-pattern, like you don't want to write C++ code like this, but it's sort of ingrained in us. If you didn't start out with C++ as your first programming language, this might be ingrained into you from other languages that didn't have things like exceptions, where you follow a code that has a particular pattern like this. You have some function that's performing some work, doing some computation. So what do you do? Step one, you perform whatever initialization is required for the processing. Step two, you actually do the processing. And step three, you clean up whatever stuff was to be cleaned up based on the initialization you did. Maybe the initialization allocated some buffers or something that are used for the computation. And at the end, you want to clean up those buffers. And it's not really important that these be function calls. Initialize just could be a few lines of code, and cleanup could be a few lines of code, and doWork also could be a few lines of code as well. But the thing is this sort of overall pattern. The problem is that if doWork throws an exception, then you never reach cleanup. And usually what happens is an important step in cleanup is that you release any of the resources that are no longer needed now that you're done the particular computation you were doing. So this kind of structure is sort of an anti-pattern. If you see this, you should kind of, alarm bells should go off saying, oh, wait a minute, like if any exceptions get thrown out, there's a good chance that bad things are going to happen. So this particular code is not what we call exception safe, meaning that if you start throwing exceptions, the code is likely to be not well behaved. So essentially what we want to look at are ways to sort of deal with this particular issue. But before that, I want to introduce a little bit more terminology. So when we're talking about code and whether it's exception safe, I mean, what we mean by exception safe, if we say that a particular operation in the code is exception safe, it simply means that if an exception is thrown when that operation is being performed, that the program will be left in a sane state. You're not going to end up with invariants of various parts of the code being invalidated or something like that. So generally, we want to write code which is exception safe, because if your code throws any exceptions and your code is not exception safe, by definition, you have code that's going to have bugs and not work properly. In terms of exception safety, there's kind of different levels of exception safety that we can promise. The most basic one is what's called the basic guarantee, which is basically just saying your code is exception safe, but I don't make any promises beyond that. I'm not doing anything fancy, but the code won't go insane if you throw exceptions. Invariants will be maintained and so on. So basically all invariants are preserved. In other words, things that sane code should be doing, like the state that things should be in, will be maintained, and no resources are leaked either. What the sort of thing basic guarantee doesn't provide is it doesn't provide a guarantee that if you're performing an operation and the operation fails, that it will leave things in a state where there's been no side effects that resulted from the partial operation that was performed. Something was partially done, but it failed, so it didn't get all the way through. In the process of getting to the point where it failed, it may have changed some of the state in the program. Maybe you're working on a container, you're adding something to the container. For some reason, the operation that adds the element to the container fails, maybe it was allocating memory. But it may have changed the state of the container in the process of doing so. So you might not be left with a container that was as it was before you try to add something to it. So a basic guarantee is just a very, as the name suggests, just a very basic minimal kind of guarantee. Going kind of the next level up in terms of a somewhat stronger guarantee is what's called the strong guarantee. And what this is, essentially has commit semantics. Or like, if you think about databases and transactions, or if you think about git and commit, like when you commit a change, either it goes through and it all goes through, or none of it goes through and you're left with things as they were before you attempted to do the commit. So this is what's sort of meant by commit semantics. So in other words, if you're performing some operation that makes a strong guarantee and it fails, maybe it gets partway through and it fails, if it changed any state getting up to the point where it fails, it will back out those changes. So it is as if you didn't ever call that operation in the first place. This is what's referred to sometimes as commit semantics. With the strong guarantee, though, what can still happen is there can still be an exception thrown. So this function, it will kind of clean up and fix things if an exception is thrown or if the operation fails due to an exception being thrown. It guarantees it will kind of back out any changes that were made. So you're left with no side effects having occurred due to that operation. But it doesn't make the guarantee that no exception will be thrown at all. So sort of the last kind of strongest guarantee of all that we can make is what's called the no-throw guarantee, which is essentially saying the operation is no except. Like it will never throw under any circumstances. Volcanoes can be erupting, major seismic events swallowing up buildings around us, but this function is not going to throw no matter what happens. Or maybe more precisely, like internally there could be exceptions being thrown all over the place, but what it won't do is it won't let an exception propagate out. Like it won't emit an exception, which from a user point of view is all you care about. If you're using some code and maybe you have very badly written code that can't handle exceptions, you don't really care if it's throwing exceptions internally. What you care about is, does it let them propagate out? Because as soon as they propagate out into your code, if your code isn't exception safe, it can't handle exceptions properly, then you have a problem. But if internally it's using exceptions, typically this is not an issue. So this is really what the no-throw guarantee is concerned with. It's saying, kind of to be more precise, it's not saying that the operation itself isn't causing exceptions to be thrown. Internally it could be, but they'll never be visible to the user. They never propagate out of the function. And as we kind of go from basic guarantee to strong guarantee to no-throw guarantee, it gets progressively more and more difficult to make these guarantees happen. And for a lot of code, there's just no hope of making it the no-throw guarantee. Like fundamentally what you're doing, there's no way that you can do what you want and guarantee that an exception could never be thrown. Any questions about any of these? So in terms of what guarantees we might want to make in certain circumstances, or maybe just a basic comment to begin with though. First of all, a function is not no except. So in other words, if it doesn't promise that it won't throw, you have to assume that it will. Because if the person who wrote the code knew that it wasn't going to throw, they would have made it a no except function to begin with. So if the no except promise is not being made as part of the API specification, you have to assume that the reason why it is that way is because it will throw. So anytime you see a function that's not no except, you have to assume it's going to throw. Then in terms of when might we want to provide the various different types of exception guarantees, well, if you're going to use exceptions in your code, it has to at least provide the basic guarantee. Because the basic guarantee, if it's not fulfilled, then basically what that's saying, as soon as you start throwing exceptions, you don't know what your code's going to do. Because invariants can be broken, your code can get into insane states and so on. So you always want to provide the basic guarantee. In terms of the no-throw guarantee, you should always provide this for destructors for reasons that we talked about when we looked at exceptions sort of in the first iteration of exceptions earlier in the course. One thing that was noted was that when you're throwing an exception, one of the important things that takes place is a stack unwinding process. And basically what this is doing is it's invoking lots of destructors, potentially. So destructors often get called when you're processing an exception. And if you throw an exception when you're processing an exception, this is not allowed and your program will be terminated by the C++ runtime. So because of this, it's generally a very, very bad idea to have destructors ever throw exceptions, because you're just kind of begging the gods to have the situation arise where you're processing an exception and then your destructor throws, and then your program's toast at that point. In terms of functions other functions that you definitely would want to have the no-throw guarantee provided by whenever you can would be operations that are basically doing moves, like move operations, and swaps can be implemented in terms of moves typically. So for move operations, so like move constructors, move assignment operators, swap operations, typically you want to make them no-throw whenever you can. In other words, you would want to make these functions no-except. For most types of classes that you'd be implementing, typically this is not a really big problem, because often the thing that causes you to want to throw an exception in the first place is you're trying to acquire resources. Like this is a big thing that can go wrong. You're trying to allocate memory, well, you run out of memory, throws bad alloc. Or you're trying to do, allocate some other resource and it can't be allocated, and then you can't maybe construct the object you're trying to construct, and then it needs to throw an exception to indicate this. The reason why move operations are less problematic is kind of the whole idea behind move that typically makes move operations much more efficient than copy operations is they typically can avoid the acquiring of resources, because what they do is they rip the resources out of the object that you're moving from, and then they drop them into the object you're moving to. And because you're just ripping the resources out of one object and then dropping them into another one, you don't have to create new ones. Maybe the only thing you might need to do is deallocate some resources, but typically this is a thing that is less likely to cause problems. I mean, I guess in principle, things could fail for certain types of resources when you try to deallocate them, but typically this is much less of a problem. So this is one of the reasons why, like practically speaking, it's usually not a big problem to make the no-throw guarantee for move type operations, although there could be some exceptions in cases of maybe very complicated types. In terms of the strong guarantee, if you can provide the strong guarantee and it's not going to cost you a lot or cost you anything, then probably it's a good idea to provide it. In other words, why not make a stronger promise if you can, if it's not going to cost the user of your code anything? Of course, if in order to make the strong guarantee, maybe you have to write your code in a much less efficient way, then probably you wouldn't want to just provide it automatically, because then the user is paying for something they don't necessarily need, because maybe they don't care if it makes a strong guarantee, but you're giving it to them anyway, but at a price. So generally, like if you can give a stronger guarantee and it doesn't cost you anything, probably you should do it because it has benefits. But if it costs something, then you have to contemplate, well, maybe I don't want to provide it because the user might not need it, and then I'm making them pay for something that they don't necessarily need. So some examples of strong guarantees that are made in the standard library, the pushback operation, which essentially adds elements to a container. As long as certain container-dependent conditions are satisfied, the example I'll use is std vector. So if you use the pushback member function for std vector, as long as the type that you're putting into the container, in other words, the element type for the std vector, as long as it either has a move constructor that doesn't throw exceptions, or it has a copy constructor, in other words, the type is copyable, the vector type makes the strong guarantee for pushback. In other words, if you try to do a pushback operation, adding something to the end of the vector, and for any reason an exception gets thrown, I mean, typically the problem would be you do pushback, there's no more capacity in the vector. In other words, the size of the vector is the same as the capacity, so it has to allocate a bigger array and then propagate the values from the old array into the new array. And of course, things can go wrong, because when you try to do that allocation, it could fail, that could throw a bad alloc exception. So if this happens, what's guaranteed by the container std vector is that it will ensure that the container is left in the state it was before you tried to do the pushback. So it's as if you never called pushback in the first place. And this sort of behavior, you can imagine it's quite helpful. Like if things go wrong, it's probably nice if it was just as if you never did anything. Like it's just left in the state that it was before. Rather than it's left in some valid state, which is a much weaker condition, right? Because if it didn't make the strong guarantee and pushback failed, if it only made the basic guarantee, for example, maybe just the container's empty. I try to push back, maybe there's 1 million elements in the container, all very valuable data I don't want to lose. I push back, it fails, and then as a result of this, it returns you, it leaves you with an empty container. This would be valid for the basic guarantee, because the basic guarantee just says I'll leave it in a sane state. An empty container is a sane state. It's maybe not a desirable sane state. It's probably not what you want, but it's valid. So this is the reason why, from the preference from the user's point of view, if it's helpful to them, would be a stronger guarantee. But at the same time, sometimes they might not need it. So you don't want to give them a stronger guarantee than what they need if there's a cost to it. Another example of something that makes a strong guarantee in the standard library is the insert member function for std list. I mean, std list is basically a doubly linked list. So if you're trying to insert a new element into the list, if for some reason it fails, like for example, it tries to allocate a new node for the doubly linked list and the memory allocation fails and there's an exception thrown, you're guaranteed that the list is unchanged. It's just as it was before. And then a couple of examples of things that make the no-throw guarantee in the standard library. If you do the swap of two containers, basically there's a swap function that you can use to swap the contents of two containers. If this is guaranteed never to throw under any circumstances. And pop back is another example. Pop back, I think, for at least most of the containers or all of the containers makes a no-throw guarantee. Any questions? So the term resource acquisition is initialization, or RAII as it's more commonly abbreviated to. This has kind of come up, I guess, a few times in the course, although maybe we haven't kind of formally talked about it. It's shown up in various contexts. Essentially, the idea here is this is a technique which helps us to, at least in part, to combat resource leaks, essentially by tying the lifetime of an object to the acquisition and release of a resource. So the basic idea with RAII is that we have some object which owns a resource, and then when we construct the object, what this will do is it will allocate that resource. Maybe it allocates memory. And then in the destructor, it will release that resource. So if it was memory, it would free the memory. So these sorts of patterns, this RAII pattern, can be very useful for helping to avoid resource leaks for various different types of resources. And essentially, again, the way that it works is it ties the lifetime of an object to the acquisition and release of a resource. And as long as you write your code correct for the destructor for this RAII class, it will have the effect of ensuring that resources always get released whenever the end of the lifetime of the object, the RAII object, is reached. Any questions about that? So on this slide, I have a code example to kind of come back to the earlier code example that we were looking at. The one that appears at the top here, this implementation number 1, was some code that we looked at earlier in this lecture. And essentially, we have this use buffer function where the user or caller has to pass in a buffer that's already been allocated, and then it does some kind of computation with the buffer. And what we observed before is that this is not a good way to write the code with respect to exceptions, because if use buffer throws an exception, and it can because this function is not declared as being no except, then this delete never happens because we get ripped out of the function before we hit the delete expression, therefore the memory gets leaked. So the question becomes, well, how can we try to combat this problem? I mean, we can start putting try blocks in all over the place and catching exceptions and so on, but a better way to do this would be simply to employ this RAII idiom. In other words, let's take the resource that we're allocating, which in this case is memory, and embed it into an object. And then we'll tie the allocation of the memory to the construction of the object, and then in the destruction of the object, we'll free the memory. And as long as we don't forget to delete the object, invoke the destructor for it, which in most cases is a local variable, so the compiler essentially does this for us, then we won't leak any of the resource. In this case, it would be memory. So what I have on this slide is just a very kind of stripped down, simple smart pointer type. Smart pointer just referring to the fact, the word smart just referring to the fact that the interface is similar to a pointer, so we call it a smart pointer. The word pointer appears there, but the smartness comes from the fact that it knows about cleaning up after itself. In other words, it can actually manage the memory that's allocated, that's associated with the pointer. So we have so what we have in this class here, it's templated on the type T. So the idea is that this type is a smart, like it's a pointer to type T. T is the type of the element it's pointing to. And what we have here is an underlying data member. There's just a single data member, which is just a raw pointer to T. And the idea is this class is essentially going to wrap a raw pointer to T, but it provides the extra functionality of making sure that the memory that's associated with this pointer gets freed in the destructor. And in the constructor, we also allocate it. So if we look at the constructor for this smart pointer type, we provide a size, which is the number of elements is actually for allocating an array of T. So like this is a smart pointer to an array of T. So the size parameter here is the size of the array that we want to allocate. So we're going to basically create an array of T, which has that particular size. And then we assign this result of the new expression to this pointer data member. Then if we look at the destructor, this is kind of the important thing, really, is the destructor. Essentially what the destructor is doing is it's deleting this pointer. So there's no way that this object can reach the end of its lifetime and you don't free the memory that's associated with it, because the destructor is always going to free this memory. And by the way, just to recall that if for some reason this pointer was null, deleting a null pointer is valid. It just won't do anything. It assumes that there is no underlying memory allocated. And let's see. In terms of there's no copy operation that's provided by this particular class, just because it wouldn't really make sense to copy, because if we allowed copying to happen, this would allow sort of multiple owners, multiple, or maybe putting it another way, it would make it sort of unclear under what circumstances you can actually release the memory. Because if there were multiple owners, multiple smart pointer objects that were deemed to be owning the data that they point to, and multiple pointers are pointing to the same underlying data, when you go to invoke the destructor would not be able to tell if there's only one owner, in which case the thing that's destroying is the last thing that's referencing that data, in which case you should free it. Or there might be other owners that are still out there, in which case you don't want to free it. So for this reason, this type is not copyable. It would cause problems with the way that the things are implemented if we tried to do this. So focusing just on the move operation, we have a move constructor and a move assignment operator. So this type is movable but not copyable. For the move, all we do is we just rip the pointer. So basically there's two objects involved here. There's star this, which is the thing we're moving to, and then there's other, which is the thing we're moving from. And what we're doing is we're just ripping the pointer out of the other object and putting it into star this. So we're ripping the guts out of one, we're ripping the resource out of one object and putting it into the other, and then we're setting other pointer to the null pointer. In other words, what we're going to do is we're going to leave the other object as being like essentially a null pointer, like a smart pointer which has the null pointer value, which just means it's not pointing to any memory. And then if we look at the move assignment operator, in this particular case, the first thing that we do is we have to delete the pointer that's associated with the thing that we're moving to. In other words, star this, because we don't want to leak that memory. So we first get rid of that memory if it's there. And then we do a similar thing as what's done in the move constructor. We basically rip the pointer out of the other object, the one we're moving from, and assign that to the pointer variable for star this. And then we set the other pointer to be null. So what we leave the pointer that we moved from in a state that it's no longer pointing to anything. It's just a null pointer. And we allow for this null value for the smart pointer, just meaning it's not pointing to anything. In an analogous way that we have null pointers for regular raw pointers, just meaning it doesn't point to anything. And then we also provide a function that allows us to get the actual pointer that's stored inside this smart pointer object. It's just a raw pointer. And that's the basic interface. Any question in terms of the code for this particular class? Okay, if we look at the code down below then, so essentially what we've done using this class up above, we're going to take the code from the top of the slide and rewrite it in a slightly different way such that we avoid these problems that if useBuffer throws an exception, then we're going to start leaking memory. So what we do here is we, instead of creating our buffer using a new expression directly and just assigning it to a raw pointer, and the problem is raw pointers, they don't know how to clean up after themselves. They don't participate in ownership. So when they reach the end of their lifetime, if they're pointing to allocated memory, well, that's nice. It doesn't get deallocated. And that's essentially what leads to the problem. So what we do down below here is instead we create our buffer by creating one of these smart pointer to array of char objects here, and the size of the array is 1024 because that's the size that this useBuffer wants. And then we call useBuffer, and we have to, the reason why we have this getMember function is we can't just pass in a smart pointer to char because that's not what the interface, what the interface is required by useBuffer. It wants just a raw pointer to char. So what we do is we provide this getMember function so that we can access the underlying pointer that's associated with our smart pointer and then pass that just as a regular raw pointer into useBuffer. And this is okay to do here because useBuffer is it's only using this pointer for the purposes of accessing what it points to. It's not participating in ownership kind of operations. Like it doesn't participate in allocating or deallocating memory. This is what it makes it okay to pass a raw pointer around. Like generally the cases where you want to use raw pointers when you're passing them into functions is if the behavior of the function is it just wants to observe what that pointer is pointing to or possibly modify what the pointer is pointing to, but it's not going to participate in the ownership sort of operations, basically allocating and deallocating of memory. And in this case here, it's kind of implied by the discussion that kind of preceded this, that useBuffer, all it's doing is it's just using this buffer for the purposes of doing some computation here, but it doesn't do any deallocation of the buffer or anything like that. So this is a perfectly fine thing to do here in terms of passing a raw pointer into this function. And then the code actually gets a little bit more clean in this respect because now we don't need to do anything explicitly below the useBuffer call to actually deallocate memory. What happens is when we fall off the end of this function, the destructor for this buff object gets called, which is then going to free the memory which is associated with this smart pointer object. And even better, if useBuffer exits due to an exception being thrown, it's still the same story. If we get ripped violently out of this function because useBuffer throws, as we're leaving and we leave this block here, because buff is a local object inside this function do work, its destructor gets invoked and then the memory gets freed associated with our buffer. So no matter whether we leave useBuffer by a regular return and things are kind of successful, or we leave by an exception being thrown, it doesn't matter. We still don't leak memory. The resource is released. So this is just another, like an example of applying this RAII kind of methodology or idiom to like a pointer kind of like memory sort of resource. Any questions? And RAI can be used for other things as well. It's not just a issue of trying to minimize resource leaks. You can also use it, for example, to restore state that's been modified. And this is an example of this sort of usage of RAII. In this particular case, what we have is a function which it takes an output stream, an O stream, and it takes some integer to write to the output stream. But for some reason, we want to output things in hexadecimal. So there's what's the word, manipulator that we can output to the output stream called hex, and also show base, which will put like the 0x in front of it to show the number base that things are printed out in. So this is basically going to change the way in which x appears when it's written to the stream. And then, of course, when we're done this, probably we don't want the entire program printing every integer that we ever print in hex, because most of the time you probably want to print things in decimal. Like for most things, that's what makes the most sense. So the code is very careful to make sure that essentially what it's doing here is when you change the state on the stream, these manipulators result in a kind of a sticky change to the stream. In other words, some things when you apply them to a stream, they're only for the next field that you output. But some of them are sticky in the sense that once you change the state for these things, they persist that way until you change them to something else. And hex is one of these things. Once you output this std hex to the output stream, all integers subsequently are going to be in hex until the end of time, or until you decide to output. There's also a corresponding std dec, meaning decimal. So this is the reason why after what we do at the beginning here is we save the flags that are associated with the stream. There's a member function called flags for O streams, which just returns the flags. So we save them here. And then just before we return from this function, we set the flags back to what they were initially. So like here we save them, here we modify them by setting the hex, the hexadecimal flag, and then we restore things back. So we have a situation where we're changing some state, but we don't want to have that state change persist, so then we restore it at the end. But again, this code is very brittle as well because exceptions can be thrown. So for example, when we're outputting X, it's conceivable that maybe underneath in the implementation of the stream, maybe it needs to allocate some memory because the stream involves buffering. Maybe for some reason it needs to allocate memory or it does something else that could potentially throw an exception. If it throws an exception, imagine that it throws an exception when it's trying to output X. So that means we've already output this thing, std hex, and we've output std show base. So now we're going to be printing numbers in hex until the end of time. Then an exception is thrown. We get violently ripped out of this function, and we never have a chance to set the flags back. So now we're going to be printing all our integers in hexadecimal, for the rest of our program, which is probably not what we wanted. So how can we fix this sort of problem? Well, again, we can apply RAII again. The basic idea here is that we're going to use some type, and there's actually a type in the Boost library that does this because it's a very common thing to want to do. There's this RAII type called iOS flag saver, which kind of does what the name suggests. It saves flags for an IO stream. So what we do is we provide the output stream here that we want to save the flags for, and it constructs an object, and all it's saved inside the data members of this IFS object is it basically looks at the flags, remembers what they are in a data member. And then what happens when this object is destroyed, the destructor for this class will say, I'll set the flags back to whatever I saved them in the constructor. So it takes the value that's saved in a data member, and it sets the flags back to that value. So this allows us to save and restore state. So in this particular case, the code actually becomes a little bit cleaner. And this is one thing you'll notice with RAII. Often the code actually becomes even, not only is it like better because it's more robust, but it makes the code actually easier to read. Because now we don't have all of this like saving and restoring state. Instead, we just have a single object that's created, and there is no explicit action that's done after we output things. It just, as we fall off the end of the function and the destructor gets invoked, what happens is the flags get set back to the way we wanted, the way they were originally when the constructor was invoked. So this would be a more safe way to do output when there's a potential that exceptions could be thrown. And even if we didn't have exceptions happening, like arguably this is still a better way to do things, because the common mistake is of course, you write the code this way and you forget this to set the flags back, right? You forget the part that restores the state. Whereas if you use RAII, you can't really forget, because at least if the variables involved are local variables, the compiler invokes the destructor, you can't forget. I mean, unless you have a buggy compiler and it doesn't invoke destructors for some of your local objects, there's no way that you could possibly forget to release or to restore the state that you want to restore here. So there's lots of cases where you may have some state that you want to save and then restore later. This is a good sort of use case for this RAII idiom. Any questions? Some other examples of RAII. There's what are called unique putter and shared putter. These are smart pointer types in the standard library. We'll be talking about them more in detail a little bit later. But these are basically used to manage memory. They're similar in spirit to kind of the smart putter type that we just talked about a few slides earlier on an example, except they're more fancy. They have a little bit more functionality, but the basic idea is the same. Essentially, they provide like a wrapper type that kind of encapsulates the memory resource that's been allocated, and then in the destructor, if no one else is going to be using that data afterwards, it will release the memory, for example. We also looked at scope lock and unique lock when we were talking about concurrency. These are more examples of RAII. In this case, the resource that's being managed are locks on mutexes. So you're basically releasing locks or releasing mutexes in the destructor of these types. I guess you could also argue things like IF stream, OF stream, and F stream, and string and vector. Also, I guess you could make the argument they're sort of RAII classes to some extent. I mean, usually when I say RAII class, I think of a class that its sole purpose to exist is providing RAII functionality, whereas these classes, they do a lot more than just provide RAII functionality, but I think you could still correctly say that they kind of use the idea of RAII. For example, these types here are used for manipulating files. So you're basically doing like I/O, reading and writing from files. And a file is a resource. When you're done with the file, you want to make sure that you close it, because typically processes will have an upper bound on how many open files they can have any given time. So if you keep opening files and never close them, eventually what's going to happen is when you try to open a file, the operating system is going to say, no, you've got the maximum number open that you're allowed, and you're not going to be able to open yet another file until you start closing them. So we don't want to leak open file descriptors either. So this kind of encapsulates that. In the case of std string, essentially this is going to be managing the memory that's associated with the string, because the string has to be stored somewhere, at least assuming that there's no small string optimization or that the string is big enough. There's going to be some memory allocated on the heap to hold the actual character array. So something needs to make sure it's freed, and string takes on that responsibility. And std vector we've used a lot in this course. Obviously, it has an underlying array that it uses to store the data in, which is, for example, allocated on the heap, which it then needs to free, and it frees this in the destructor. So these last three bullets are types that are not like purely only doing RAII, but they're still using the ideas from it. Any questions about any of this? Just a few comments about whether it's appropriate to use exceptions in certain circumstances. So exceptions are a useful tool, but they're not necessarily something that you want to use in all circumstances. So what I want to point out are some situations where maybe you wouldn't necessarily want to use exceptions. One of them might be in situations where you have very limited memory on the system that you're working on, for example, maybe some kind of embedded system. Often, and again, it depends on how exceptions are implemented. There's more than one way that they can be implemented. They're quite a complex thing. But a lot of implementations, they sort of make the trade-off that they want things to be sort of more time efficient in terms of exceptions, and the price that you pay is it takes more memory. There's a memory cost involved. And this is the way that a lot of implementations, at least my understanding of it, is they kind of lean in this direction. So a lot of implementations, there's a non-negligible memory cost if you're using exceptions. Maybe even if you don't throw exceptions, the fact that the code actually, is compiled with exceptions enabled can start to use memory. And this could be in certain situations where you're very tight on memory, this could be unacceptable. Another situation where you may not want to use exceptions is if you have a situation that happens frequently. You wouldn't want to try to signal this by exceptions. Exceptions are really meant for exceptional cases, like things that happen infrequently. Because exceptions do incur a fair amount of cost, when you throw exceptions, it takes quite a bit of effort to handle them. Because of this, you wouldn't want to use it to signal some kind of commonly occurring case. Another situation where you might not want to, or probably wouldn't want to use exceptions, is if you have some kind of time critical code, like for example, you're writing some kind of a hard real-time application, like code for a hard real-time application. The problem is once you start having exceptions be thrown, it gets difficult to say, like how long does it take to get from point A in the code to point B? If you're just looking at it and there's no exceptions thrown, well, kind of all the control flow you can actually see, because like in order for a branch or something to happen, you need an if statement or a loop. But as soon as you start introducing exceptions, you can have control flow all over the place that's implicit. Like it's not explicitly there in your code, but there are branches and things happening because of handling the fact that exceptions could be thrown, and you could return from a function because an exception is thrown and so on. So because of this, it can sometimes become very difficult to predict, like how much does it time, in the worst case, can it take to get from line A in the code to line B when there can be exceptions happening in between the 2 points. And often in like hard real-time applications, there'll be parts of the code where you have to be able to upper bound. Like worst case, how long does it take to get from line A to line B? Because maybe this is controlling a nuclear reactor, and line A corresponds to you've detected that there's about to be a meltdown if you don't do something, and line B is like things have melted down if you haven't done anything by this point, and you want to make sure that getting from A to B is not going to take too long. So exceptions can sometimes make it more difficult to analyze the code to figure out, like in the worst case, how long can things take. So this would be another situation where you might not want to use exceptions. Another place where obviously you wouldn't want to use exceptions is if the code base that you're working in is not exception safe. So maybe you're dealing with some old legacy code that was written a long time ago before people thought exceptions were very important. So they wrote everything assuming no exceptions were thrown, and because of this, probably really bad things are going to happen if you start throwing exceptions. So in this kind of situation as well, you probably wouldn't want to start throwing exceptions. Hopefully you won't encounter this situation yourself when you go to graduate. Hopefully you won't be working with any really old legacy code bases where basically the entire code base is not exception safe. But unfortunately, there is stuff out there that's like that. Anyway, any questions about any of this stuff? In terms of enforcing invariants in code, so basically by invariant, I just mean things that should always be true. So certain classes may have invariants, conditions that are always true that associate with maybe some of the data members in the class. If you detect in your code that some invariant has been violated for one of your classes, for example, how might you signal this? I mean, one obvious thing you could do is you could use an assertion, like you assert that the condition that should be true, the invariant you're testing, is true, and if the assert fails, well, then this will terminate your program. Another possibility is you could throw an exception if you detect that some invariant has been violated. It's kind of a gray area, really, whether you should enforce invariants with exceptions versus assertions. But one thing that I would caution you about is that I think sometimes students, when they learn exceptions, they get a little bit overzealous that they want to use exceptions sort of all over the place. One of the main differences between using exceptions versus assertions kind of, there's a lot less work that you need to go through to get out of the program and terminate and print an error message compared to the amount of things that exceptions have to do, because it has to go through all the stack unwinding process, et cetera, et cetera. So if you imagine that you've detected some invariant has been violated, and maybe the thing that you've detected means there's a really good chance that, for example, a stack has been trampled all over. If the stack has been trampled all over and then you try to do stack unwinding, it's probably just going to go into deep space, because if the stack has been trampled all over and corrupted, there's no hope that stack unwinding is going to work, because it's basically got to walk along the stack and kind of, as the name suggests, unwind things, kind of undo what's been happening. So I guess the advice that I would give is if you detect something is wrong in the code and the thing that you've detected is an indication that probably things are fairly badly hosed, in other words, maybe there's a good chance that if you threw an exception that probably it's going to die anyways because it's not going to even be able to do the exception handling, then probably it'd be better to use an assert. I mean, even with an assert, if things are badly hosed enough, there's still no guarantee that you can even print an error message and terminate properly by calling, typically it calls std abort, the assert function, and prints an error message. There's no guarantee even that can happen, but at least there's a lot better chance that that can happen because there's a lot less things that need to happen compared to the processing for an exception. So that would be the general guidance I would give. And some people ask questions on some of the assignments that sort of related to this, and this was generally the type of advice that I gave. Anyway, any questions about that? Yeah.
So asserts also are used for testing, so sometimes people will turn them off for release. Is there so did you double up and have both an exit condition and an assert? Or?
I guess this is another kind of bonus for assert as well. Like if you have an exception in the code, then there's not an easy way to just kind of turn it off. Whereas with assert, you can easily turn it off if you don't want to do it. I guess another impact I didn't think about with respect to exceptions is they change the API. Because if you might throw exceptions, then you can't make those functions no except. Maybe you'd kind of like to, but you can't because now they need to be able to throw. So they can also have an impact on the API. Anyway, sorry, go back to your question.
Also, the question I was asking is that, like, in the event that you have all these errors that you can't really recover from, it's probably best that you just abort now or do something similar to that. But if you were using asserts and they got turned off during the build process, then you may have let your program keep running while it's in an invalid state for a lot longer. Is there a solution?
Right. Well, I guess then you could start to make the argument, well, maybe if I really still want to catch errors in that case, then maybe I do want to use exceptions or some other mechanism other than assert.
Yeah.
I mean, there is kind of no perfect answer, right? There's trade-offs to both ways, and there may be other additional ways other than just using assert and exceptions, but these would be probably the two main go-to, like, obvious approaches you could use. Yeah. This is why I say it's kind of gray. So yeah, if you were going to sometimes ship things maybe to the customer and you're turning assertions off because otherwise it maybe affect performance, but you still want some kind of indication of what went wrong if things failed, then maybe you need some other kind of mechanism. But you could also add like logging or other things as well that might not use exceptions and also not use assert. So there's other ways to do things as well. Anyway, any other questions? Better stop here. I'm running over time.